Okay, we're gonna get started with today. Welcome back. It's me again. So I'll see you on here on Wednesday, but this week we are doing Astropy. Before we get started, see this our overview. Yep. Homework 9 is due this Wednesday. Homework 10 was released, and then it'll be due next Wednesday. Okay, cool. Great. So here are the warm-up questions. They're very similar to last week, so hopefully you solidified the content a little bit for your brain. No worries if not, but just take a couple minutes, close the laptops, just try and guess. It's okay if you don't remember, not the end of the world. Yeah, and then I forgot to upload the file, but I'm going to put it in B courses. So then once we're done, just put that in your directory for today. I don't know these questions on this. Yeah, because of this derivation class completely regarded. Because you just know before you officially the lowest here. It's like driving these. Let's say you do a lecture. Well, I should have this first. And then I mean, No, it's not. Okay, let's get started with today. Alrighty. So, um, question: how do you import curve fit into a Jupyter notebook? Yeah.
From SciPy to optimize import for the
Perfect. Yep, just like that. Great. Okay. What's the difference between popped and peacock?
Opt is the optimal parameters and PCOV is the covariance matrix.
Great. Great. Yeah. Weird terms. Okay. What does it mean to mask your data? Yeah.
You're like choosing a like a certain area of data to like analyze more intensive data.
Great. Yeah. Great explanation. And then also you could think about it as like getting rid of excess data that you don't want. But yeah, if you really want to focus on one portion of your data, great. Okay. And then we didn't quite cover this one a ton last time, but why would you use an initial guess in your curve fit function?
Does it just reduce the time it takes to generate the function because it starts somewhere instead of starting from like no reference?
Great. Yeah, exactly. So initial guess is just that. If you have like, okay, I think it's generally like this sort of direction, you're like pushing SciPy to go there, so it takes less time. This is especially helpful if you're running like thousands and thousands and thousands of data or like data files and all this crazy stuff. If you can give it an initial guess, you can really cut down the time. So yeah, very helpful. Great. Okay, so let's get started. I put a file in vCourses under like demos. It's called data.fits. Question?
I was just wondering, like, what is covariance matrix?
Yeah, great question. So we're not, it's a bit above the pay grade of this class, but you're welcome to take data 8. But essentially the covariance matrix, we use it to get the errors on the fit.
Okay.
So we have like a line of best fit, and that would be our optimal parameters. That would be like our slope and our y-intercept. And then the covariance matrix basically tells us like, okay, how good of a fit is that slope or that y-intercept?
Okay.
Yeah, no, great question. Okay, cool. Great. All right. So yeah, pull up a Jupyter notebook and we'll get started. Okay. Give me a thumbs up when you are ready to go. Thumbs down. Okay, thumbs up. No thumbs up. Yes. Great, yes. So there's a file. So if you go to files and vCourses under the lectures and demos, I put a file called data.fits. Download that and put that into your directory. Is anyone having trouble finding it? Okay, cool. Great. All right, so we're gonna do some fun things. So, okay. We're learning the package Astropy. And just to give you some context, so I always like breaking words apart in like physics and stuff and try to like understand what we're doing. So hence the name we have Astro. We gotta like turn this. Okay. Astro, which means well, it means stars, but essentially it's astronomy. So this is a Python package related to astronomy, and then we have Pi, which stands for Python. So astronomy plus Python. Hopefully that gives you enough context. NumPy, in case it's like NumPy, that was numerical Python. So just for some context of what we're doing today, this is really astronomy coded. So if you're more math, engineering, physics is still, I would say, very relevant, but this is more on the astronomy side, but it is very helpful for FITS files, which are a very common data type. Okay, so what can you do with AstroPy? What can you do with Astropy? It has so many functions, like a lot of cool stuff. So I'm really only going to teach you the essentials of what I use in the package. So one of that is units. And you're like, oh boy, units, so much fun. No, but it actually is really cool. So it's really great with units. Then we'll do some constants. which also sounds kind of boring, but it is also very helpful, especially if you're doing a lot of math. And then, last but not least, we're going to learn what a fits file is. And then you get to plot a really cool thing in your Jupyter notebook, which honestly was one of my favorite things I did in the Python decal. And then we'll do a little bit of image processing. That sounds scary, but we're really just going to look at like the details of our image and try to get some information out of it. Okay, so um, with that, we are going to start with units. So the first thing I'm going to do is I'm going to import a package. So I'm going to call from Astropy. I'm going to call import units as u. So Astropy is the package. Units is the like subdirectory that I want inside of it, and then I'm just calling that u. Okay, so that is what I want. If you are getting an error, when you raise your hand if you're getting an error with Astropy, because that might happen to some of you. Anyone running into an error? Okay. Is it saying it's not installed? Yeah. So if that's happening to you, you'll want to do %, pip install Astropy. So if you're getting a thing like cannot find Astropy, just try running this right here in your notebook. That still doesn't work. You'll have to come to office hours and we can take a deeper look. But if you're on Anaconda, it should work. So is anyone getting an error when they try to import Astropy? Thumbs up if it works. Okay, we'll keep going then. Great. So that's what we'll call. So I'll just comment that out because I don't want to run that. Okay, so I'm going to run from Astropy import units as u. So I'm going to make a variable called distance. Then I'm going to set it equal to a value. I'm going to call it 1e to the 5th. And then I'm going to give it a unit of kilometers. So we have a variable, which I'm calling distance. We have a value, which is 1e to the 5, but this is also 100,000. And then we have a unit, which is u.km. So with Astropy, we're essentially adding on a new step to our coding. So no longer do you just have a number, but essentially now you can change not the data type of your data, but you kind of can add a data type in a weird way. So you can add a unit, and this is very handy. Fun fact I always like to tell when teaching Astropy is that late 1900s, not really that far long ago, NASA was like, hey, let's send a mission to Mars. And it was like the Mars, I can't even remember what it's called, but it was like a Mars mission, and they sent it off, but it was a collaborative project. So they worked with scientists in the UK. And if you know something about America is that we use really weird units like feet and inches, whereas the rest of the world uses like centimeters, meters, kilometers. So two different scientists working on the project, one of them used imperial, one of them used metric. And then when they came together, they accidentally crashed the lander right into Mars. So they literally built this beautiful satellite. They spent decades on it. They were able to get it off the planet Earth without it exploding. They got it all the way to Mars. They were about to like orbit around, and then it crashed right into the surface. I think it's the Mars Climate Orbiter. Can't remember. But anyway, that was because of units. Only because of units. They got a mistake with how far away Mars was. They thought it was further away than it actually was. So they crashed right into the surface. So they just used Astropy, you know. Maybe we could have learned more about Mars on that mission, but it happens. So units are very important. Okay, enough with that story. So getting back to the Python. So velocity, we're going to name a new variable. And I'm going to set it to another quantity. So we'll do 20 kilometers per second. Okay, so now I'm going to run these. So now if I print distance, you'll see that it comes attached with a unit now. So if I didn't have this kilometers right here, it would just print 100,000. But now I'm adding this, so Astropy prints that extra kilometer. So I can also print velocity, and it gives me the kilometers per second. Okay, are there any questions about this setup? Nope. Okay, let's keep going. So we just attached units. So we now we're gonna do a new. We're gonna now if you just wanted the unit or you just wanted the value, we can attach functions. So now I can print distance times value, and that would once again just return me the number. This is very important if you're working with Astropy data, because when you try to use Astropy with NumPy, it's not going to work. You have to get rid of the units. Well, in some cases. So just keep that in mind, but this is how you can get the unit back out, or the value back out. So retrieve, or let's see, get back just the value. But we can also print distance times unit. And that gets back the unit. And it just gives us kilometers. So handy little functions to use, but highly recommend. Okay, so now let's combine units. So now I'm going to make a new variable called time, and I'm going to do distance divided by velocity. So when I print my time, I will now get a unit of seconds. So to slow down, distance, I told it was units of kilometers. And then I said velocity was units of kilometers per second. So then if I do distance divided by velocity, then I get kilometers. And then you get like over kilometers times seconds. So just your unit conversion. Yeah, so these guys cancel and we're left with seconds. Great, so that's what we did. So if we wanted to figure out how far we went in that distance with that amount of speed, we would have, it would take us 5,000 seconds. Though I don't really know how much 5,000 seconds is, so what we can do is we can convert our units. Okay, so does anyone else still need to copy this? Okay, question to above this? Yes. Is this an okay pace, or do people want me to go slower? Good? Okay. All right. Anything else people need to copy? All right, let's keep going. So, great. Let's convert units. So let's go from seconds to hours. So what I can do is I can call a new variable called time. I'll specify the unit, and then I'll say, zoom in, time dot to u dot hour. So then if I print my time hour, I get it converted to about 1 and almost a half hours. So 1.5 hours. So that's how long it would take me. So that's just a brief introduction to units with Astropy. I use this for my physics homework when they're like, derive this equation and then plug all of these numbers in. And it's like, oh my goodness. And then like you make a small mistake and you get deducted points. Highly recommend using Astropy to check your work. So yeah, okay. So let's do a practice question. So, oop. Okay. Okay, so on your own, just take a few minutes, try and answer these questions with Astropy, what we just did, and then we will come back together. You're welcome to use this Astropy documentation, but just try and not just immediately Google the answer. Okay, who needs more time? Okay, just a couple of hands. All right, well, I'm just gonna get started so that we don't run out of time, but we'll have more practice on Wednesday. Okay, so with that, we'll do our practice question. So, I asked you, okay, with distance, velocity, and time, convert distance to AU. Okay, so can someone tell me how do I convert distance to AU? Yeah,
Well, distance dot two and then U dot A.
great. I'm gonna just make a new variable, just because it's good practice. But yeah, great. Okay, so then let's print distance AU. Great. So now we have it in AU. Don't know why you'd want such a small number, but if you're doing solar system stuff, that's great. Okay, so now I want to convert velocity to meters per second. So I'll just do this one. So let's comment that out. Okay, so we have velocity in meters per second. So then I will call velocity dot two, and then whoop, u dot m, and then u dot second. And then if I print this variable, I get it converted to meters per second. So you can do this with multiple units at once. You don't just need one. Cool. All right, and then the last one for one was convert time to minutes. So I'm going to do time underscore minute equals time dot to u dot min. And then let's print and see what it gives us. Great. Okay, so that's just some extra practice, just moving around the units. Great. Okay, so now can someone tell me does anyone else need to copy this? Good? Okay, cool. So next question. What happens if I print velocity plus distance?
There's an error because they're not.
Great, yeah, exactly. So we'll do it, and then we'll comment it out. So velocity plus distance. And then if I run that, oh, yep, it gets upset. So yeah, it'll catch you if you have the wrong units. So just make sure you're not doing that, but great. So gives you an error. So, okay. All right. Last question was, okay, so I say travel time equals 500 kilometers divided by micrometers per second. Okay, so I'm going to call that out or type that out. So travel time equals 500 times u dot km divided by 100 u dot m, sorry, meters, not micrometers, u dot s. Okay. Oop. Sorry, this needs a, cool. All right. Ah, I'm running out of space. We'll zoom out just a little. Okay, so there we go. There's my travel time. So let's print it. Let's see what I get. Travel time. Nope. Okay, 5 kilometers per second per meter, which cancel out. So I get seconds. Now, if I just wanted the units, I can print travel time dot unit. And there I go. I get kilometers second per meter. And then I say convert travel time to seconds and minutes. So yeah, I don't like this weird like kilometers over meters thing. That's just confusing. So let's get rid of that. So I can instead call travel time equals travel time dot to u dot s. Oh, sorry, I already put it in seconds. Did I give you in seconds? I did say seconds. Okay, whoops, my bad. Okay, cool. And then we will do 2 hours. Actually, yeah, I forgot. This isn't going to get rid of our weird problem, but it's fine. I'll leave that as an exercise to the reader. Okay, travel time dot to u dot. Did I say hour? I think I said hour. Okay, cool. Oh, it does get rid of it. Okay, cool. That's what I thought. Yeah, so, great. Okay, are there any questions? this is just playing around with units. We're not really doing anything too very exciting yet. This is not like plotting, which is very fun. But maybe this is fun for you. Okay, so any questions about units? All right, let's move on to constants. So next chapter for the class, constants. We're going to import a new package. So from Astropy, import constants as const. Great. Okay, so that's the package we are going to import. Or I guess directory, but whatever. Okay. Now I am going to call a new variable. So I'm going to say mass, and then I'm going to give it a unit of kilograms. Okay. Then, if I want to, well, okay, to show you where we're going, we're going to do E equals mc squared. And instead of writing out the speed of light, we can instead have Astropy just import it for us, in case you don't remember what it is. So I'm defining my mass here. So this is my m in my E equals mc squared. So m equals mass, c, well, I already read that below. C equals speed of light. So good. So this is my mass. It's in units of kilograms. All right, cool. So then I'm going to define a new variable called speed of light. Then I'm going to call constant dot c. So if I print that, it gives me 2.99, etc., 10 to the 8th meters per second. That's the conventionally accepted, experimentally tested speed of light. So that's great. So now let's put it to use. So I'm now going to call energy equals mass times speed of light, and then I'm going to square that. And then let's see what it gives me. Perfect. I don't really know what that means, but it's great if you're doing like, I don't know, hydrogen fusion and you want to figure out how much energy you're going to get out if you're able to use all of the mass from the atom, or the difference between your 4 hydrogen atoms and your single helium atom. So yeah, great. Okay. All right. And then if I wanted to convert this to a different unit, so this is E equals mc squared. This was our constant provided by Astropy. Great. So now I want to convert from weird units to joules. So I am going to call energy underscore J equals energy dot to U dot joule. And then I can print that, and I get more conventional units. But once again, I don't really know what a 10 to the 16th joule means in this context. But anyway, just playing around with stuff. So yeah, great. Okay. Any questions about this? All right, I'm going to keep going. So Astropy also gives us lots of information about our constants. So information from constants. So I can print speed of light. And recall, I set it equal to this guy. So it's not actually just calling this variable is always going to give you that information, but this is your context. So context. Okay, so printing speed of light tells me the name, speed of light in a vacuum. This is the value. Uncertainty is 0, which I guess is good. Meters per second, and then whatever it's referencing. So yeah, that's pretty fun. And then I'm just going to comment that out. And then we can do print print speed. I don't want to have to copy that again or write it out. Speed of light dot value, and gives you just the value. And then if you want just the unit, you can do unit, and it provides just the unit. So provides just the value of C, and then provides just the unit of C. Okay. Any other questions about constants? Okay, time for another practice problem. So I'll let you add it. Okay, so on your own, just try this out, and then we'll come back together, and then we'll keep going. So yeah, try that on your own. If you want me to go back to the Jupyter notebook, just let me know as well. do we need more time? Raise your hand. Okay. Okay, so let's get crack-a-lackin'. Great. Okay. Pull back up my notes. All right, so actually I need to look at what I asked you. Okay, so calculate the energy in joules for 5 kilograms, 1 gram, and 1 solar mass. Okay, so I'm going to start by defining my 3 masses. So let's see, practice question 2. Okay, so I have mass 1, which I will call 5 times U dot kg. So this is in kilograms, so 5 kilograms. Then I have mass 2, which will be 5 times U dot G, which is 5 grams. And then mass 3, which is 5 times, and then I tell you how to do this, but const dot m underscore sun. And then this is 5 solar masses. So 5 times the mass of our sun. Okay, cool. All right, can someone tell me how can I convert mass 1 into joules? Yep, mass 1. Sure, let's try it out. Okay, how can we debug? Close, that's better. I'll give you a hint. We have to use a very fancy equation. But thank you so much for giving your answer. It was very, very close. Yeah.
Just do really like log 2 there, 14 bracket, log 2 bracket, log 2.
Gotta go a little slower. But you sound like you're on the right track.
The same here.
Okay. Great. Yes. Okay. So then we'll do speed. So times speed. Oh my gosh. Speed of light. And then we will square that. And then we'll do dot 2 U dot joule. Okay. So let's see what that gives us. Great. Okay, cool. So yes, you're very close with the U dot joule. That's exactly what we needed. But unfortunately, Astropy isn't quite smart enough to know it only needs to add a constant to get it into units of energy. But we can just do that. So then we'll just copy this for the other 2. So just boop, boop. So energy 2, energy 3, mass 2, mass 3. I'm not going to print them out because you can do that. But yeah, so that's how we would do it. Great. Okay, so I'm going to skip the next one. We'll come back to it if we have time, but I want to leave room for FITS files because I think they're very important. Okay, so we will maybe come back later. Okay. All right. So moving on, let's talk about FITS files. So let's see, what does the acronym stand for again? Okay. Yes, so a FITS file stands for FITS equals flexible image transport system. So, interesting words used here, so we can break it down. So flexible, I mean, I feel like, they're trying to do something here with that. It is very flexible, it's very nice. But basically it has a bunch of functions that we can do to it. Image. So we're gonna be looking at images. So you're gonna have images on your computer, which is really fun. A lot of astronomy is taking pictures of the night sky. That's what FITS files are. They're pictures of the night sky. Transport, moving stuff around between different systems, between different people, different projects, collaborators, and then system, system. So yeah, FITS files. A lot of you will use them in your final projects. So this is where we learn how to import them. Okay, great. So let's move on from that. So we're going to call a new function. So from astropy.io, import fits. And then we're also going to import matplotlib. Matplotlib.pyplot as plt. Cool. So, all right, this is our new function. Great. So I'm going to type some stuff out. You might just need to copy it down, but then you'll see what it does. So with fits.open, you should have a data file called data.fits. So put that inside, and then as hdual. Ignore what hdual means for now. You don't really need to know. You're welcome to look it up on the Astropy documentation, but it's just what you'll see when you look up Astropy and how to use it. It'll basically open files and call them hduals, which stands for something, but I can't remember what it is. So yeah. Okay, so that's your first line. Then inside of data, so who has heard of the word metadata? Okay, a couple of people. So if you go on your phone and you take a picture of something, and then you scroll down, it'll tell you when you took it, where you took it, the size of your image, all of that stuff. That's called metadata. So astronomy pictures also come with metadata, and you can access that with something called a header. So we're going to call a variable called header, and then set it equal to hdual, and then we're going to index it by 0 and say header. So accessing metadata information. Okay. Then we're going to call another thing called data. You'll never guess it's the data. And then hdual 0.data. Okay, so great. That's our first step. Now we're going to do something really fun. And then I'll go back and explain what the above stuff was, but I think this is cool. So plt.imshow for image show. Then you're going to plug in data. Then I recommend using a color map called plasma. Okay, and then plt.show, and then run and see what you get. It's pretty cool. What is it? Does anyone know? Anyone recognize what it is? Yes. Great, exactly. So if it takes a second, great. Here it is. But the first time I took Python decal, we did this image, and I was like, oh my gosh, we can plot pictures? I'm like, yeah, you can plot pictures. Pretty cool. So yeah, this is the Horsehead Nebula. This is just a free image that Astropy provides, so I just downloaded it from their site. There's so much data that you can play with if you want. So that's the Horsehead Nebula. Now, let's do a little bit of image processing with it. So pretend we went out in our cool telescope and we took an image of the night sky, but yes. Of course. No, yeah, I know, it's very fun to get the cool image. Okay. See, can I get everything? Almost. Okay. Great. So I'll just talk through what this stuff is. So hdual, that's essentially like our image packet. You can think of it like a little packet of information. That's what hdual is. 0 is we are indexing that part of the package. So if you think of like a book, it has chapters in it. Our entire book is in this file. However, there are different chapters in books. So we're accessing the first chapter, or the 0 index, because Python starts at 0, not 1. So this is the first chapter. However, if you've heard of something called stacking, you can basically put a bunch of data inside of one file. So we can access basically different images by changing the index number. However, there's only one image here, so we don't have that. But some of your data some of the data you download off the internet might have data stored at these different indices. So you're welcome to dig into that with the headers. So yeah, okay. Are there any questions about this? Great, let's keep going. So, now if I wanted it, yeah, okay, we'll do it this way. Okay, so if you go on into astronomy in labs, they will basically have you plot pictures on a logarithmic scale. So, images are usually plotted on a logarithmic scale. So, log scale, let's see. That's a fancy word for instead of counting by, okay, let's see. Normal scale is you have 0, 1, 2, 3, 4, etc. Like these are evenly divided in terms of 200 to 800. A log scale instead starts at 0, then it goes to 1, then it goes to 10, then 100, then 1,000, then 10,000, and then you just keep going on and on. So that's called log scale. It's very common in astronomy. If you ever worked with the Hertzsprung-Russell diagram, HR diagram, that is plotted as a log scale. They might not have told you that if you took Astro C10, but that's a log scale. So we're just gonna play around with that, but no worries if you are so confused. So matplotlib dot pyplot import log norm. This is just a package. There's so much in matplotlib. I think Pranati posted the in the awesome plotting guide or whatever. It explores a lot of new things we haven't done in this class, so I highly recommend checking it out if you like plotting. But plt.imshow will plot our data. Then we'll use a new color map. We'll do gray. And then we'll do norm equals log norm. Cool. And then we'll do a color bar. And then we'll do put.show. I should have done a color bar above, but it's fine. Okay, so I'll give you a second to copy that down. For some context, while we're plotting this in gray, is because actually when astronomers go on sky, which means use the telescope to take pictures, they don't get the pretty colored images that you see from NASA and Hubble and JWST. Those are actually have been processed. Most images from the night sky are monochromatic. That means one color. Yes. Okay, maybe they have to try a different package, but yeah, no worries. It's not a huge deal. So, okay, cool. So, we can try something else, but yeah, okay. Let's see if it works for me. Okay, mine's upset as well. Oh well, but you can plot. Oh yes, nope. Okay, but you can plot it with log norm. There are other ways, but yes. Okay, so moving on. I'll come back to this later. All right, so log scale basically it makes the brighter stuff brighter and the darker stuff darker. So you can see more fine details. Okay, so now we'll do a little bit more of image processing. So sorry that this didn't work. But yeah, okay. Coming back to that later. So I want to call my file data.fits. And then I'm going to call this again. You'll see why in a second. Fits.open as file. And then I just want to look at the info. So basically we're repeating what we did above. So repeat from above. But now I specifically want the information from my image. So when I plot that, it tells me that I have information in different locations. So this is the dimensions of my image, which makes sense because if I scroll back, well, I won't scroll up, but you saw that it was 800 by 893. It looks like we have table of the data, which basically just means that tells us how intense our pixels are. So we'll play around with that in a second. It just tells you the data type. So this is an integer, it's 16 bits. Remember, if you go way back to very first lecture, we talked about data types. Integer is a data type. But yeah, great. Okay, I have 5 minutes. So just to show you, just like we did with pandas, so recall pandas. Pandas, we found we found the shape of our data. We can also do that with Astropy. So if I call print, I can do data dot shape. That gives me that 893,891, which is also posted right here. And then I can also print the type of my data. So if I do that, you'll see that I get, well, okay, I imported it differently this time. But yeah, so it is a NumPy array because Astropy builds off of NumPy. Okay, great. So, okay. All right, so a little bit more of image processing. I have 3 minutes. Okay. Now we're going to import NumPy as NP. So we can also find the minimum of our data. So if I call np.min on the data, then I would, sorry. Yeah, why didn't that work? Sorry, print np.min on our data. Then that is the lowest pixel value we have. So if you think of like really bright pixels as having a lot of numbers, pixels that are less bright have smaller numbers. And then if I want to print the maximum of my data, I can print np.max, and that's the value I would get. Okay, I'm gonna just quickly write something else, and then I'll let you have time to do your engagement. So, a lot of times in astronomy, you care about how many pixels are a certain brightness. Um, this is just like for fun. You don't need to know how to do this, but okay, so I'm gonna plot a histogram. So histogram equals plt.hist, and then data.flatten. So I'm turning a 2D image into a 1D image, bins.auto. So I'm gonna print this, and then I'm gonna talk about what it does. Auto, not defined. Did I not? Oh, sorry. This needs boop, and then boop. Okay, so to zoom out. So in image processing, a lot of the times you care about the distributions of your pixels. So on the x-axis, we have basically flattened the image, and this is basically all of our pixels laid out. Basically, if you can think of a snake as it's like going across the image, like 0, 1, 2, 3, 4, we basically like flattened out the snake onto our grid, and then this is how bright our pixels are. So it's very helpful when you do more heavy image processing. We're not going to get to that, but we'll have more practice on Wednesday. But anyway, so I'll post your engagement, and then are there any questions from today? I know the last part was a bit fast, so yeah. Yes, did you fix it? Ooh, thank you. Okay, cool. Let's see if it works. Yes, there we go. Okay, thank you so much. Very much appreciate it. Cool. All right, great. So. Okay, I just uploaded your engagement. I'll make an assignment on Gradescope. But with that, have a great rest of your day. I will see you on Wednesday for more Astropy. But yeah, yeah, okay.